Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to this lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 4 of module 1, wherein we are discussing the conductance and its aspects. Friends, in our previous lectures, we have seen the Venn effect, Debye-Falkenhagen effect, uh, then we have seen the Walden's rule, we have seen ionic mobilities, velocities, and the migration of ions uh, wherever the electrodes are not attackable. Now, in this lecture, we will proceed with the remaining part of the previous lecture. So, friends, in our previous lecture, we have seen the migration of ion in case when the electrodes are not attackable. We have taken the example of platinum electrodes, and then we have put the 4 cases, wherein the first case is of absence of electric field, second case is the variation of cations kept stationary and anions are moving with some speed. Then third case was cation and anions, they are moving with the same speed. And then fourth case we have kept that anions are moving with double speed than cation. And then we have seen their movement, and then we have seen that the central compartment concentration remains same, and the respective electrodes they get discharged at the respective electrodes. Now similarly, in herein from this lecture we will see the migration of ions when particularly the electrodes are attackable. Now in our previous lecture we have taken the examples of platinum electrode because they were not attackable. Now we can take the example of copper or silver electrode wherein they become attackable, and when particularly we take the solution of silver nitrate and the silver electrode they become attackable, and we can see the variation in concentration in particularly this case. So let us consider the case of the silver nitrate solution, wherein the silver nitrate is getting electrolyzed between two silver electrodes, isn't it? These are the silver electrodes. Now these silver electrodes are attackable. So whenever the excess nitrate ions come in contact with the electrode, they attack the silver electrode and take out the silver ions from these silver electrodes, and particularly they increase the concentration in a particular compartment. Okay, so accordingly, as we have seen in previous cases, there are 4 cases. Previously, as we have seen, there are 4 cases. Case 1 becomes wherein no electric field is applied. 4 cations and 4 anions are present everywhere in anodic compartment, in cathodic compartment, and in central compartment. And since no electric current is flowing, nothing is happening in case 1. Now in case 2, let the silver ion is stationary, that is U is equal to 0, and the anion nitrate ions are moving with the velocity V is equal to 2. Now in unit time, the two anions migrate from the cathode compartment to anode compartment. You can see here, isn't it? Now as a result, there is a fall of concentration of anion in cathode compartment, isn't it? While there is an increase in concentration of anion in anode compartment. Okay. Now the concentration of central compartment is going to remain same. Herein we can see that the two excess cations are discharged at the cathode. Okay. And the two excess anions they attack the silver electrode and take out two silver ions from the electrode. Hence, the concentration of anode compartment increases by 2 units, while that of cathode compartment decreases by 2 units. You can see here the concentration of anode compartment and concentration of cathode compartment. Okay, so it has been increased by 2 units. Similarly, if I see the another case wherein cations and anions both are moving, both of them they are moving with the same speed. So let the cation and anion are moving with the same speed, that is U is equal to 2 and V is equal to 2. In this case, two cations move from anode compartment to cathode compartment, and two anions from cathode compartment to anode compartment. And therefore, there are 4 excess opposite ions in each compartment. You can see here. So cations get discharged at cathode, thereby they increase or they decrease the concentration of cathode compartment. Anions attack electrode and therefore 4 silver ions are pulled from the electrode, isn't it? And the concentration of anode compartment increases by 2 unit. So the concentration of central compartment is going to remain same in this case also. The another case is fourth case, wherein say if anions are moving with the double speed as compared to that of cation, that is I say U is equal to 1 and V is equal to 2. In such case, there is excess cation concentration of 3 cations in cathode compartment, which get discharged at the electrode, and there is excess anion concentration of 3 in anode compartment, which attack the silver electrode, thereby increasing the concentration of anode compartment. And as usual, the central compartment has the same concentration. Now from these 4 cases, we can again make some conclusions. What are those conclusions? We can make the conclusion that the number of cations and anions discharged at both the electrodes are always equal, irrespective of their speeds and types of the electrode. Secondly, we conclude that the concentration in the central compartment always remain constant. And finally, we can make the conclusion that the fall in concentration around cathode is always equal to increase in concentration around the anode. You can see in each of these cases, isn't it? So we can find out that way the increase in this anodic compartment because of the decrease in the cathodic compartment of concentration. Okay. So now, if previously as we have seen in case 3 and in case 4, if you see, it is seen that there is a migration of cation from anode compartment to cathode compartment, correct? Now even after that, there is increase in concentration in anode compartment, correct? So in order to determine the increase in concentration in anode compartment, if no silver ions would have migrated, a copper or say silver coulometer is placed in series with the cell and the deposition of silver can be recorded. So see, this coulometer is particularly, you can prepare a coulometer very easily. You can take a glass beaker and you can take in that glass beaker this silver nitrate or copper sulfate solution. And if you are taking silver nitrate solution, take silver electrode. If you are taking copper nitrate solution, you can take, or if you are taking copper sulfate solution, you can take copper electrodes. And you can actually find out, the deposition of silver or copper on each of the electrode, or you can actually measure that how much percentage or what is the fraction of transference of the particular ion from the electrode, one electrode, and the constant increase in concentration to the other compartment, that we can record. Now in order to record these transport of the ions, there are certain methods we will see hereafter one by one. This transfer of ion and transference number, it is very interesting by now, because we have seen that depending on their speed in the solution, these cations or anions, they carry current with them. So when electric potential is applied to an electrolyte solution, the ions present in the solution start migrating towards the opposite electrode. Now with that, current starts flowing in the solution, and ions which are present in the solution, they are actually the carriers of the current. However, both the cations and anions, they do not carry equal current, we know, and therefore the fraction of total current which is carried by specific ion is called as the transport number or transference number of that particular ion. It's very specific and very significant important phenomena and interesting phenomena, because whatever is the fraction which is being carried out by that particular ion, say cation or anion, whatever fraction it is being carried, it is called as its transport number or transference number. And in this case it becomes very interesting to know what is the fraction it carries with it, and experimentally it is that way little bit easier, or it is viable in laboratory to find out what is the fraction of current which the particular ion, cation or anion is carrying. And therefore let us see here the transference of ion or transference number. So let I call it as u and v be the velocities of cations and anions respectively. So if u is carrying u is for cation, so the current carried by cation is proportional to always u, because u I have represented for the cation, and the current carried by anion is say proportional to v. So the total current will be proportional to u plus v, because cation, how much fraction cation is carrying, how much fraction anion is carrying. So the total current will be u plus v. So now my transport number in this case, because I need to find out what is the fraction of current that is being carried by a particular ion with respect to the total current carrying capacity of the solution. My transport number of cation particularly will be given by T plus, and for cation it is U upon U plus V, because U is represented for cation and V plus for anion. So in the denominator total current carrying, and in the numerator the current carried by the cation. So the transport number for cation will be given by T plus is equal to U upon U plus V. Similarly, the transport number of anion is given by T minus, and it is being given by a fraction of V upon U plus V, correct? Because V is the current carried by anion upon the total current carrying capacity of the cation and anion. And therefore, if I take the sum of transport numbers of cation and anion, T plus and T minus, it should come 1, correct? Correct, because there is no other entity which is responsible for carrying current. So if this is true, if I solve this u upon u plus v upon u plus v, so again it will give me u plus v upon u plus v, and it is going to give you 1, and therefore the total current carrying ions which are present in solution are cation and anion only. Now if I take the ratio of transport numbers of cation and anion, I get this u upon u plus v into u plus v upon v, and it gives me u upon v. And this is known as u upon v is known as speed ratio, and it is denoted by r. This particularly u upon v is known as speed ratio, and it is denoted by r. Now if it is denoted by r, and if my T minus is the transport of current by the anion, and it is represented by n, suppose I say that T minus is represented as n, so T plus will be obviously 1 minus n, because T plus T minus is nothing but 1, and therefore if T minus is n, my T plus will be 1 minus n. Okay. Now if I take the ratio of 1 minus n upon n, that is T plus upon T minus, it is R, that we have seen just now, that it is a speed ratio. I can rearrange it, 1 upon n minus 1 is equal to R, and therefore 1 upon n is equal to 1 plus R. Okay, that way, and from this particular equation I can calculate, that is n is equal to 1 upon 1 plus R, that is T minus, that is the fraction which is carrying fraction of current that is carried by the anion is given upon 1 plus R. That means it is in terms of speed ratio I can represent the transport number of anion. Now in terms of cation, that is 1 minus n, it is 1 minus 1 upon 1 plus R, and therefore it is equal to R upon 1 plus R. So my current carrying fraction of cation, that is 1 minus n, is given by this. So now what we have done with this simple solving of or simple rearrangement is that we have represented both, that is the fraction which is carried out, fraction of current which is carried by the anion, fraction of current which is carried by cation, both of them they are represented by a single parameter, that is the speed ratio R, which will be helpful in solving the numerical particular portion, or wherever we know the speed ratio, we can calculate their individual values from using this particular expressions of 32 and 33. Okay, let us see now the particular experimental measurement of the determination of transport number. There are two very famous methods for this. The one particularly is known as Hittorf's method of experimental determination of transport number. You can see here the experimental assembly of Hittorf's method. It seems very interesting, as we have seen in previously the migration of ions. Similarly, based on the same concepts of migration of ions, you can see here there are three compartments. We have arranged the compartment A, compartment B, and compartment C, and using the same principle of the cases wherein we have considered when the electrodes are attackable, when the electrodes are not attackable, and in these situations we have calculated the transference of particular ions, cations or anions, and we can calculate the transport number of the particular ion in the solution. And this is a particularly very interesting experiment in the laboratory to perform, and you can actually witness how the ion carries the current and how ions they transport from one compartment to other compartment, and actually they get deposited they get deposited on one electrode and get leached out from the other electrode. Basically, the assembly used in Hittorf's method, it consists of two compartments connected as U-tube, which is the central compartment, as shown in this figure here. Now, it is further connected to resistance, battery, and a meter. Okay, each tube is connected with a stopcock. You can see at the bottom. Because why this stopcock is here? The stopcock is here because we need to take out this particular solution from any of the compartment, and so that we can titrate the given solution, and we can find out what is the strength of the solution at any particular moment or any particular event. Okay, with this particular stopcock, we can remove the solution from the bottom from any of the compartment, and we can find out the concentration of the solution from any of the compartment at any moment. Now, to determine the amount of total electricity, say silver voltmeter or copper voltmeter, which is also known as coulometer, is particularly used. You can see this particular part is known as coulometer or silver voltmeter. In this case, silver nitrate solution is used, and therefore silver voltmeter is taken. If copper sulfate solution would have taken, we have used copper coulometer. A standard part of procedure also I would like to describe over here. We can perform in the laboratory. Basically, in the standard procedure, firstly what we do, we fill the apparatus with the electrolyte solution whose transport number are to be determined. Let in this particular case we are studying this silver nitrate solution, and therefore AgNO3 solution is filled in the apparatus. Okay, now this solution is standardized with the suitable reagent in order to determine the exact concentration. It is very necessary, because unless we know what is the standard strength of the solution, it will become difficult for us to calculate what is the loss or what is the gain of particular ion in the given compartment or known compartment at later stages. And therefore the standardization of the electrolytic solution is very important. So it is done based on the suitable method. Now, if silver nitrate is used, it is titrated with standard KSCN solution, sodium potassium thiocyanate solution, and we can determine the strength of AgNO3 solution. Now, this gives the concentration of silver nitrate before the experiment that we perform. Next, we can actually start the electrolysis by passing about say 0.01 ampere current for about say 3 hours in the solution. Now, after 3 hours, we can actually see what has happened. because two electrodes in the copper coulometer, they were connected, and the current has been passed for 3 hours. So now we have to see what actually has happened. So after 3 hours, tap A is closed, is at this moment tap A is closed, and the solution is removed from the anode compartment. Okay, and its weight is taken, and it is titrated with the same titrant that we have used for the standardization. Now the weight of silver or copper, whatever it is, deposited in the voltmeter is also determined from this, and this solution in the central compartment is also removed and titrated with the same titrant to check whether the concentration is same or not for the central compartment. It should remain unchanged because we have seen the migration of ions. Central compartment concentration should always remains unchanged. Now if there is a change in concentration, we have to repeat the whole experiment. But then if the concentration is same, the calculations are done after the titration, and these calculations can be carried out. uh, let us understand what are the calculations that has been carried out. Okay, now in this case, the case one, we can consider that if the electrodes are not attackable. Okay, say for example, if we have used the platinum electrode, so what would have happened? So let us say if the electrodes are not attackable and platinum electrodes would have been used. So in this case, the weight of silver deposited at cathode in voltmeter is, say, suppose x grams, and weight of anode deposited is, say, suppose a gram, and weight of silver nitrate in anode solution that we have earlier standardized is, say, suppose b grams, and therefore we can calculate the weight of water in anode solution, that is a minus b grams. So quite obvious. So we can make the ratio calculation. So if a minus b grams of water is associated with the b grams of silver nitrate after electrolysis, so suppose the same water contains c gram of silver nitrate before electrolysis. Here we should consider C is always greater than B due to the fall in concentration, and therefore we can actually calculate the fall in concentration in anodic compartment, that is equal to C minus B grams of silver nitrate. Correct. Next, in terms of silver, so the fall in concentration will be C minus B into 108 upon 170 grams of silver. Okay, and it be at let us denote it as Y grams. So now this is the fall in concentration after migration of silver ions. So if no migration would have taken place, the fall in concentration would have been equal to the weight of silver deposited in the voltmeter, which is nothing but x grams. And therefore the transport number of silver ion is equal to the fall in concentration of silver in anodic compartment upon total fall in concentration in both the compartments. So it is nothing but, it is transport number of Hg is equal to y upon x, and transport number of nitrate ions is nothing but is equal to 1 minus y upon x. So this is how we can calculate the transport number of silver ions and nitrate ions using the non-attackable electrodes like platinum electrode. Similar is the case when we can imagine the case wherein the attackable electrodes are used. So the second case is if the electrodes are attackable and the electrodes are of silver electrode. So if we call it as a silver voltmeter, so my weight of silver deposited in cathode is, say, suppose x grams. Weight of anode solution is a gram. Weight of silver nitrate in anode solution is b gram. So weight of water we can calculate a minus b grams. So again the same principle. So a minus b grams water is associated with b grams of silver nitrate after electrolysis. So suppose same water contains c gram of silver nitrate before electrolysis, and here C is greater than B due to increase in concentration due to attack of nitrate ions, and therefore increase in concentration in anode compartment is nothing but B minus C grams of silver nitrate. So then in terms of silver, increase in concentration is B minus C into 108 upon 170 grams of silver, that is Y grams. Now this is the increase in concentration after migration of silver ions. If no migration would have taken place, the increase in concentration would have been equal to the weight of silver deposited in the voltmeter in this case, that is x gram. So fall in concentration due to migration of silver ions is x minus y, and therefore the transport number of silver ion is fall in concentration of silver in anodic compartment upon total fall in concentration in both the compartment, and therefore the transport number of silver ion is x minus y upon x, and transport number of nitrate ion is 1 minus x minus y upon x. So this way we can calculate both the transport numbers in this case wherein the electrodes were attackable. If copper voltmeter is used, the amount of copper is converted into equivalent amount of silver by multiplying 108 upon 31.8. That is the only difference if copper coulometer has been would have been used. So this is how I can actually calculate the transport numbers based on the principle of Hittorf's method. Let us see some of the one or two numericals based on whatever we have seen just now. It is just a revision of the concept that we have seen just now. Let us say first numerical is very simple, wherein the speed of ratio, the speed ratio, that is R, of silver ion and nitrate ion is given as 0.88, and we have to calculate the transport number of these ion. So we have seen earlier also that the speed ratio is calculated as T plus upon T minus. So this ratio is given as 0.88, and we know that the transport number of this nitrate ion, that is anion, is n. So this n is given by n is equal to 1 upon 1 plus r, just now we have seen. So if I substitute the value of r over here, I get the transport number of anion, that is nitrate ion, is 0.53, and 1 minus n is going to give me the transport number of cation. So transport number of silver ion is 1 minus n is equal to 1 minus 0.53 is equal to 0.47. So I can get very easily, I can calculate this transport number of cation and transport number of anion and transport number of cation using this speed ratio values. So if I know the speed ratio, I can very easily calculate the transport number of cation and anion. So in any numerical, if it is given if the numerical is given with the speed ratio, I do not require the transport number of individual cation or anion. I can calculate from the speed ratio individually. Similarly, just now we have seen the Hittorf's method, and based on the Hittorf method, just one small numerical we have seen. Now herein what is given in an experiment based on Hittorf's method, KCl solution was electrolyzed between platinum electrode. That means platinum electrode is used, that means electrodes are not attackable, and therefore we can use the formulas we just now what we have seen in the case where the electrodes were not attackable, and using those formulas we can calculate the fall in concentration in the anodic compartment, and then we can calculate the transport number of cation and transport number of anion. What is given? It is given that 0.0137 gram of chloride was lost from the anode compartment, and 0.0857 grams of silver was deposited in the silver coulometer connected in the series. So they determine the transport number of K plus and Cl minus ions. So first what we have to do, we have to convert it into gram equivalent. So number of gram equivalent of chlorine minus Cl minus lost from the anode compartment is 0.0137 upon 35.5. It gives you 3.859 into 10 to the power minus 4 grams equivalent of chlorine. So now this much chlorine has been lost from the anode compartment. And what is gain in the coulometer? So gain in the coulometer is because of the transport of both the ions, and therefore the total number of gram equivalent deposited in coulometer, if I want to calculate, it is actually given 0.0857 divided by 108 as a silver coulometer, since we have taken silver coulometer. So it is actually 7.935 into 10 to the power minus 4. So if I want to find out what is the transport number of cation, I can find out the loss in the anode compartment divided by the total gain in the coulometer. So it is 3.859 into 10 to the power minus 4 upon 7.935 into 10 to the power minus 4. It is going to give me 0.486. And since I know the transport number of cation, I can find out the transport number of anion as 1 minus 0.486, that is 0.514. So this way I can find out the cation, transport number of cation and transport number of anion. We can actually solve many numerical. We will see definitely the numericals based on without methods wherein the electrodes are attackable, and other numericals as well. But first we will see one by one the other methods like moving boundary method. But in this lecture we will stop here. So friends, we will stop here in this lecture. In our further lectures, we will see the other methods of transport number, particularly the moving boundary method we will see in our next lecture. Thank you.